Hi. In this video, we're going to be finishing our discussion of chapter 14.1, which is the introduction to functions of several variables. In the previous video, we finished talking about how to graph their domains. And now we're going to talk about graphing the actual, graphs. It's a pretty basic process. It's going to be very similar to chapter 12 and pretty similar to the last video. We're going to start by setting the function, if we have two variables, equal to z. What if we have more than two input variables? We're not going to graph it. Again, if we have more than two input variables, that means we need at least 4 dimensions to graph it, and we're not going to do that. We don't know how. It's not something I don't know how to do. It's not something you don't know how to do. It's something that's pretty much impossible for creatures like us. We're going to try to get, or rearrange to see a known surface. Okay, like a known quadratic surface, paraboloid, ellipsoid, hyperboloid. Okay, as painful as that would be. We're going to get something, or cone, right? That's another common one. And if all those fails, we'll use a computer. If needed. Now, because of how useful this is, if it's not an in-class test, if it wasn't an in-class test, I'm not going to ask you to do this probably, because you could just get an image from a computer. Now, you should still learn how to do this. It's not that bad, but it's not the most important thing in the world, because, I can't draw either. But like I said, it's really not going to be that bad, right? Like, you don't need a computer for our first example. I don't need a computer for our first example. You don't either. 6 minus 2x plus 3y. What does that look like? Who knows, right? Maybe if you see this for the first time, you're not entirely sure, but you can replace that with a z. And then when I say arrange things to get an, that looks really ugly. I mean, I can read it, but rearrange. I don't know why I'm writing so small today. So if we have z equals all that junk, when I say rearrange, a lot of times in this class, we've had all of our variables on one side, and we set it equal to a constant. Let's see what we would get in that case. We'd get something like this. Do you recognize that? I know I do. If we have a linear situation, which in this case, my x and y are both linear, multiplied by, constants, and maybe we have an initial constant somewhere else in there, I know what that's going to create. Because the 3D equivalent of what were lines in 2D is a plane, right? Is a plane where one of the axes, one of the dimensions, is constrained by the other two. That means we're going to have a 2D input, a 2D domain, and a 3D output. So this is going to be a plane. And for planes, we can find the intercepts. Intercepts. 2x equals 6. X equals 3. Negative 3y equals 6. Y equals negative 2. Z equals 6. Done. And we're just going to try to give this a graph and see what it looks like. Wow, that was a bad line. And it was such a bad line, it made it into a curve. Yikes. Okay, well, there we go. Let's see, 1, 2, 3. In the x direction. Negative 2 in the y direction. And 1, 2, 3, 4, 5, 6. And so it's a plane that contains this triangle. Right? And so our triangles are always a good description of planes, because as you learned in chapter 12, every triangle determines a plane completely, right? We'd have the normal vector, we'd have anything else we wanted to get. So it's the three-dimensional plane that contains that triangle. Done. So I mean, you don't need a computer now. Maybe, especially if you slept through chapter 12, you'd feel more insecure if you had f of xy equals 9 minus x squared plus minus y squared. Well, never fear. Z equals. And I don't know. This is the kind of thing that maybe gets a little harder. But think, do we have 2 variables or 3 variables, right? In terms of our 3D surfaces. We have all 3 variables. So then if we're going to graph it by hand, it needs to be one of the 6 quadratic surfaces we have. All right, are all 3 squared? No, that really limits it. And there's a constant that even further limits it. One way of writing this, so I've seen 2 strategies from students over the years. We have the strategy where we can separate out a negative like this, because some students see that more naturally, right? If we started off with z equals x squared plus y squared, that's a parabola. It's a paraboloid, elliptic paraboloid, circular in fact. What's this negative to? That's going to flip the paraboloid upside down, right? Instead of opening in the positive z direction, like this does, this will open in the negative z direction. What's this do? That's a shift up 9 in the z direction. So that's a standard form. That's how I think of it. So we're talking about a paraboloid opening to the negative z direction and then shifted plus 9 on z. The other way I've seen students like to think about it is you keep the x squared plus y squared positive. Like you get everybody on one side, and then we're really talking about the other side, x squared plus y squared equals negative z plus 9. And then it's the same kind of thing, okay? Then it's the same kind of thing. You just have to learn that it would mean, it got flipped over in the z direction because the negative's attached to the z stuff, and then plus 9, still the same thing. Okay? I don't know which one will make more sense to you. I would say you're used to doing it this way. You could factor out a negative, okay, and then I know this is a paraboloid, and then it's plus 9. What I'm thinking of when it's like that is your old friend, y equals negative x squared plus 9. Right? I know what that looks like. I hope you do too. But if you're not used to that, maybe this new system would make more sense. All right. Either way, I know how to draw a paraboloid, I think, on a good day. I know how to draw shifted up 9. It's actually easier than you think, especially if you took calculus with me. We talk about, shift up by 9 is just calling something 9 and then opening down from there. You should think about what its intercepts would look like, what it would look like in the xy plane. In the xy plane, where will it hit? Where will it end up landing? It'll end up landing on 3 out. So, why? Because we have... Sorry, I'm just trying to draw my paraboloid. Nope. Because if we set the z equals 0, if we set the z equal to 0, we would have x squared plus y squared equals 9. And that looks like a circle. Opening up wider and wider as we get down here. Okay, elliptic paraboloid. Ta-da. It goes on forever downward, just to be clear. All right, let's look at a really ugly one, right? 1/2 square root 36 minus 9x squared minus 36 y squared. Okay, first step, call that z. Multiply both sides by 2. And then how are we going to get rid of that square root, right? We don't like these square roots. Not great big fans of that. Well, we'll just square both sides. And you might notice you have, all 3 variables. All 3 of them are squared, and there's a constant. At one point in your life, you knew what that was, even if it was 5 seconds while you're watching that lecture. You knew what this was. Again, we like all 3 being on the same side for most of these, unless one's not being squared, right? We would divide by 36, and you could get x squared over 4 plus y squared plus z squared over 9 equals 1. This is an ellipsoid, a 3D, ball. And we can find its intercepts, and we can try to graph it. Again, even without a calculator, even without, bad habits, even without a computer, we can understand that on the x-axis, the intercept should be 2 and negative 2. On the y-axis, we should be talking about 1 and negative 1. And on the z-axis, we should be talking about 3 and negative 3. Now, I call that y, z. On the z-axis, will we ever have the negative z coordinates? Will we ever have the negative z coordinates? I want us to focus on right here, this step, squaring, is what you always have to be suspicious of, right? This eliminates information. Info. And originally, g of x, y is only greater than or equal to 0. Why? Because the square root is only ever positive. So realistically, this is not the full ellipsoid. It's only the top half. Now, old story, how do I know it's the top half? Because again, I'm getting positive z coordinates. I'm only able to get positive z coordinates because the square root's only ever going to have a positive range, a positive output. So I'm actually not going to need that down there part, so to speak. We're going to get this kind of a shape. I guess that could be solid. Right? So I know it looks a lot like a paraboloid. It's really not supposed to. It's smoother than the paraboloid. The paraboloid does have a bit of a, not sharpness necessarily, but a vertex. This does not supposed to have a vertex, right? Like a ball. It's supposed to be pretty smooth around the top. I don't know how to describe it. Does that make sense? We're not going to go below the xy plane, because if we go below the xy plane, we would have negative z coordinates. But only the top half. So the other thing we want to understand in terms of our graphing is level curves. So level curves are basically the 2D curve obtained by intersecting planes parallel to the xy plane with a 3D surface. At different levels. Or z values. That's what a z level is. We're talking about what height are you going to intersect it. If we graph the graph of level curves in the xy plane is a contour plot. So the book definitely has some good pictures here, but we'll do a few. So if I have a paraboloid, and I intersect this paraboloid at a height of z equals, I don't know, 3, it would cut off a pretty clean circle at that height, right? If this is the plane z equals 3, it's parallel to the xy plane because it has no x and y in it. It's cutting off that circle. So the level curve, and I'd graph it in the xy plane, would be a blue circle. Okay, if it's the guy I'm thinking of, it's with radius 3. And that's contrasted with if we graphed a different plane. Like if I graphed another plane slightly lower, it would be root 3. It's the one I'm thinking of. Let's see if you understand why. I'm thinking this is the x squared plus y squared equals z. Okay. If I graphed a little lower, maybe at a height of 1 would be easier, we'd get a tinier circle with radius 1. And sometimes we'll label that as k equals 1 versus this is k equals 3. And if we do this enough times, you'd have a bunch of rings that are showing you what happens as we go along different heights. The most common thing you'll see here is like an elevation. Oh, wow. Elevation. An elevation plot. The most common use of contour plots is if you go on a hike, you might get a map of a mountain that looks like this. And each of these corresponds to different elevations. And the reason this is important is because this starts to give you an idea of the rate of change and how this rate of change could be different depending on how you approached. Going up this, it's pretty not steep, I'll say. Right? It takes a lot longer of a walk going that way to get to 400 feet. Whereas if I go this way, the walk is pretty short. Here, the walk from here to here, and here to here, and here to here are all pretty nice and symmetric. And that's going to be because of the functions we have. So I'm not saying this level, this contour map is for this function or this function. This is some other weird mountain that has a nice gentle slope going that way, but a pretty steep slope going that way. Okay? even if that didn't make any sense, the big idea is that to graph them, a level curve, set f of xy equal to k. All right, where k is just going to be some number. So for example, our function like this, 16 minus x squared minus y squared. If I'm trying to talk about the level curves here, we're going to replace f of xy with k. And just the same thing as we solved for z, we can try to solve for k and see what kind of things happen. And we might notice that we'd have x squared plus y squared equals 16 minus k squared. One way to start seeing this. So what happens? When k equals 0, we have a circle with radius 4. Okay, and we can pick other nice numbers. But in general, do we see how as k gets bigger, increases, what happens? The circle's radius, or the radii, decrease. And we're going to stop when k equals 4. Just the point, x equals y equals 0. Right? X squared plus y squared equals 0 is only, just so you can see it, that is only solved when x and y are both 0, right? If x and y are anything else, it's not going to happen. Nothing's going to happen. So what do the level curves look like? Okay. When k equals 0, we have a circle with radius 4. That's what it looks like when the plane is intersecting with the xy plane. Like that's what this surface looks like when it intersects the xy plane. Like this is the actual intersection with whatever surface we have and the xy plane that I'm actually drawing. And then what happens is we get smaller. And smaller. And smaller. Until we just get the origin. Okay, and what the square root does is it does change how quickly things grow toward the center, but again, because of how symmetric everything is, because these coefficients are balanced, we're going to end up having a normal growth rate. It won't be a situation, all the paths should be the same amount of steepness if I could draw a circle, right? The problem is I can't draw circles, so it looks weirder, wibbly, wobblier. Okay, and this is what we're trying to think about. Just how does turning that knob, adjusting the k value, change the graph at all? So a better example of what I'm talking about, of how things can get affected, is something like this. Okay, because now k equals y squared minus x squared, well, things are certainly going to change. If we have k equals 0, we'd have x squared equals y squared, or y squared equals x squared, which is y equals x and y equals negative x. So 2 lines, weird. K equals 1, we'd have 1 equals y squared minus x squared. This is a hyperbola, if you remember our chapter 2 discussion, chapter 12. What about k equals negative 1? Because k can definitely be negative values here. what would happen? We're not really supposed to have a negative 1 there. So we'd have to switch it to 1 equals x squared minus y squared. This is also hyperbola. So what is happening? What are we graphing? And these are the same questions you should remember from chapter 12.6. I suggest you go watch that video if this really sounds completely unfamiliar. Because we're talking about a situation where if we're above the xy plane, we're getting hyperbolas where the y is major. Both of these are what's happening when the k equals 0. It's k equals 0. When k equals 1, we have, and when k equals negative 1, we have hyperbolas like that and like that. Excuse the bad drawing. So what is this? This is the elliptic hyperboloid. This is the goofy looking saddle function, the Pringle function. Something like that. Where when we are below the xy plane, we're looking like that. And when we're above the xy plane, we're looking like that in the y direction. And in the xy plane, we have that kind of saddle. So, saddle. Picture it however you want. You can go back to 12.6. You can look at GeoGebra to see what this actually looks like. But this is the same discussion we were having in 12.6. I do want you to know that. All right. The main reason we're interested in this is not just to review 12.6 or to watch Mr. Leven struggle at, I don't know, drawing hyperbolas, drawing the ellipsoid, drawing the elliptic hyperboloid. There's also this notion of level surfaces. Okay. Now, what's that? This is the intersections of spaces with 4D curves, 4D graphs. So just like the intersection of planes with 3D functions, 3D surfaces gives us curves, an intersection with a 4D guy, a 4D graph will give us surfaces. As weird as that is to think about, this is the only access we have of kind of generating an idea of what's going on in 3D. Okay, so for instance, if I have f of x, y, z. Whoops, plus 1. All right, now don't get twisted. This is not a plane. Why is it not a plane? Because when I go to substitute the function with k, you'll notice there's 4 variables. Now, k is supposed to be a constant. K is supposed to be a constant. So if we want to get this into a normal plane type form, k minus 1. And these would all be planes. So the level surfaces are a family of planes with normal vector equal to 2, 4, 3, right? That's what they all have in common. So if I wanted to draw that, I would need 3D space. And now I'm not drawing the domains. I'm certainly not drawing the graph itself. That would be one level surface. And then what would happen as k got larger is each of these would increase. Each of these would increase. And so what we're talking about here is what this 3D function is doing. And each of these planes are a spot where the output's the same. One way of understanding that is this is like a space. This is the region of our 3D space where all the points have the same temperature. Okay, and that creates a 3D surface. Or all the points have the same gravitational pull. That would be a level surface of a sphere because of how the law of gravitation works. It's just a radius outward from the center of mass. So here we'd be talking about all of these points along those planes have the same temperature or the same force or the same color, right? They literally have the same color. But that's the sense in which they're the same. That's what these level surfaces are telling me. And this is the only access we have of understanding what these 3D functions do. Sorry, these 4D functions do outside of some of the calculus techniques we'll be able to achieve. Like you will still understand how to do the calculus of the function. It's actually a lot easier than graphing it, at least for me. But the point is that's the only access we have to what this looks like. It looks like something where this graph would be the same along the plane. The output along that plane is always the same number, that same k value. That's what we're controlling. By controlling this k value, we're saying all along this spot, those points have the same z value. These points have the same z value. These points have the same z value. Like it's clear when it's 3D. What is this saying? All of the points on this plane, not just the triangle, have the same w value, or the same temperature, or the same force, quality, however you want to think of it. I hope that makes sense. As always, feel free to come and talk about it in office hours some more if it doesn't. And thanks for watching. Bye for now.